Oh.
And I say, okay, then I just ask the thing, okay, I'm at index 5 now, tell me what's stored there. Yeah?
So then the add would it just be n plus n, or would it be n squared for the worst case? Because you're considering the iteration as well.
Oh, if you count the iteration, it wouldn't be n squared, it would be n plus n. Right? It could take cost n to get there and then to do the insertion. The reason I separate out the cost of getting there and the cost of doing something is when we look at linked lists, that becomes important. With linked lists, just getting at an index, random access is expensive in a linked list, right? Because you have to traverse it. On the other hand, if you're already iterated to the right spot, then it's cheap. But I get a little ahead of myself here. So that's the insertion. So what's the cost of doing a get on an n-element linked list? So I say, give me what's at index 3 or something, or index 100. Certainly not constant. The list is n elements long. Oh, I'm sorry. We're talking about the best case. Yeah. You're right. Best case is constant, yes. What's the worst case? That's linear, because you may... What is the worst case? Right in the middle. Because n's not the worst case, because I got a way to get there quickly. But right in the middle, you got to come in from one end or the other. It's going to take n over 2 steps to get there. So that's linear in the worst case. What about adding to the end? That's constant, because you can just go to the end in one step, because I'm assuming I got a reference to it, and then just add there. And what about in the worst case?
Still constant.
Still constant. What about the cost of iterating through an entire linked list? Yeah, that's just linear, because we just follow the links. Good. What about, as we're iterating, suppose we're iterating through, and we say, hey, what's stored at this one right here? Constant. If you're already pointing at the thing, if you have a holder reference to the thing, it's going to be constant time to get it out. And what about if I say, hey, I'm here now, add something after where I'm pointing?
Constant.
Constant. Okay. And, okay. So any questions about that? Let's compare. So on the left we have dynamic array, on the right we have linked list, and I've highlighted the differences in red. So we see the dynamic array is better at random access. So the get operation is theta of 1 versus theta of n. On the other hand, the linked list is better at insertion on the add operation. Because in the worst case, it's linear for the dynamic array, whereas it's constant for the other guy. There's one more difference. The add last worst case looks worse for dynamic array, but is it really that bad? What's misleading about that theta of n?
It doesn't occur very often.
It doesn't occur very often. So we got, you know, if you start out with a one-element array, you get to do an add last, and that works. The next one, you've got to double it and copy it. Then you get a couple more before you have to double it and copy it. Now you've got like maybe 4 more before you have to double it and copy it. So the expensive operations only happen every now and then, and they get further and further apart as the thing gets longer, but they also get more and more expensive. So what would be maybe a fairer way than looking at absolute worst case? What would be a fairer way of looking at the cost of an add last?
Average age?
Maybe an average case, maybe averaging over a bunch of insertions. Yeah?
Maybe I just don't understand the point of theta, but wouldn't you just be able to say that the worst case is all of them and kind of infer that same thing?
Well, what if I said the worst case is O of n for add? Why, I mean, I could say that and it would be true, but it wouldn't be as strong a statement as theta of n. Yeah?
Because it could be faster.
Right, big O just gives an upper bound. So if I say it's O of n, that leaves up the possibility that it's actually constant time. Now if I say it's O of n and that bound is tight, it would mean the same thing as theta of n. When I say this, it means the upper bound is O of n. I mean, it's O of n and it's omega of n. It is n. So let's analyze a little harder on add last right there. So this is what's called an amortized analysis, the style of analysis we're about to do. So we're going to look at the cost of k consecutive add last. The idea is you start with an empty array list, and you add k elements. What is the average cost of an insertion? What's the cost of those k insertions? What's the cost of k consecutive insertions? So we're going to assume that the dynamic array starts out with room for one element. So initially, the dynamic array is empty. The internal array is of length 1. There's room to store 1. To make the analysis simpler, we're going to resize it as soon as it fills, as opposed to resizing it after it's filled and we're attempting to add another element. So what we're analyzing is actually worse than reality. The doubling happens a little earlier than it has to. It just makes the analysis simpler. So we're not going to be underestimating. We're going to be overestimating, if anything, the complexity. And we're going to count the cost of the add last. I call it an append operation. Doing the add last when the doubling operation doesn't occur is going to be A. And when we have to resize, the cost is going to be R for each element that's involved in the resize. Each element has to be copied. So that's how we're going to do our accounting in terms of A and R. So A is the cost of just appending a new element to the array list when the doubling doesn't have to happen. And then there's the resize cost. And we will see that the worst situations will occur when we get a power of 2 number of elements. That's when the doubling occurs. So it occurs when the first element's inserted. It'll occur after 2 elements, after 4 elements, after 8, after 16. All right, so here's a table. So what I've done is, on the left I'm talking about the operations that are occurring. And after that operation, I say what the size of the thing was, of the array list. And in the last column, it's the cost for all the operations on that row. So the first thing I do is an add last. That makes the array go from size 0 to size 1. And the cost of that add last was A. A is just the cost of an add last. It doesn't, it's just the cost of the add last exclusive of the doubling. But now because the array is full, we've got to resize it. So that add last triggers a resize. How many elements are copied? 1. And we said that the cost of a resize was R times the number of elements copied. So that's where the R comes from. So this is, what happened to my, this is the cost of the add last, this is the cost of the resize. Okay, now we add one more element, giving us a size of 2 at a cost of A. One more add last is an A. That triggers a resize. There's 2 elements, the array is full, so it's got to double to 4. How many elements are copied over? 2. That's all that's in there, and that's a cost of 2R. We're paying a cost of R for each element that gets copied over. Right? So now we have 2 elements. We add 2 more to fill the array to reach a size of 4. So that's a cost of 2A. 4R for the copy. Now 4 add lasts get us to 8. That's a cost of 4A. So this is always 4 times A. 2 times A. And then, forget where I was I here? Anyway, let's say I'm here. The resize 4 elements are copied over, we get 4R. And you can see how this goes. Every power of 2, we pay a certain cost to get to that point, and then a cost for the insertion. And it keeps going down. You can see we're going 1, 2, 4, 8, 16. So the next, if this weren't here, what would be the next row in the table?
2K.
Well, forget about K. Right. It would come down to 32. How many add last would be required to get to 32? 16. What would be the cost of those 16 add last? 16A. And what would be what about the copying cost?
32R.
32R. Okay? So the pattern continues. Then we get here. We do 2 to the K add lasts. What will be the size of the array after we do those 2 to the K add lasts? 2 to the K plus 1. Because it doubles each time. So the previous time it would have been 2 to the K. can also see, we do 8 add last, multiply it by 2, that's the current size of the array. We did 4 add last to get us to 8, so we did 2 to the k add last to get us to double that, 2 to the k plus 1. What was the cost of those 2 to the k add lasts? 2 to the k times a, and then that triggers a resize. And what's the pattern that you see? It's always that the cost of the resize is, the coefficient for the resize is twice the coefficient for the adds up there. So what's this going to be here?
2 to the k plus 1.
2 to the k plus 1 times r. So what was the total cost of all this work? How do we determine that? The total cost of starting with an empty array list, and ending up with an array list of size 2 to the k plus 1. Yeah?
Do you take the cost and multiply with the operations and then add them?
Well, simpler than that. What do we do? Where are the costs in this table? This column. Each row is the cost of the work we did on that row, right? This is the cost we did just for the resize. This is the cost we did for that resize. This is the cost we did for these add lasts. So what's the total cost? Just add them up. Add up all those things. So let's do that. So the cost of the add last looks like that. I did a little factoring. That first A is sort of an outlier, so I just had the A plus, look at the coefficients, 1, 2, 4, 8, up to 2 to the k, times A. Okay, all right, if you add the first k powers of 2, what do you get? Add 1 plus 2 plus 3, 1 plus 2 plus 4. 7. 1 less than 8. What's 1 plus 2 plus 4 plus 8? 15. 1 less than 16. What's the pattern? It's 1 less than the next power of 2. Handy thing to know. That's sort of the handy thing to know, just like the sum of the first k integers is k times k plus 1 over 2. So I can replace in this the 1 plus 2 plus 4 plus 8 up to 2k with what? 2 to the k plus 1 minus 1. And let's see, I do a little simplification. Basically end up with 2 to the k plus 1 times a. But why is that not a surprise? That the cost of the a, that the a's were 2 to the k plus 1 times a. We really didn't need the table to figure that out. It's a number of elements, and each one paid a price of a to get into the array list. Okay, let's add up the r's. Okay, it's a little bit different. The final term is not k, it's 2 to the k plus 1. So what's that sum going to sum to? All right, so this mess right here is going to be 2 to the k plus 2 minus 1 times r. And so add those together, we get that, and the rest is just, a little bit of rearranging, and we get that. Okay? So that's just the sum. Now I sort of want the average cost, the amortized cost per add last operation. What's the average cost of an add last? So I want to divide by 2 to the k plus 1, right? That's the number of add lasts that we did, 1 for each element. So I just do the division, and when I divide total cost by the number of add lasts that we did, I get this. A plus 2r minus this thing here. So where do I get off saying that's constant time? That the average cost of an add last operation is constant time. Yeah?
So the a and r are constants, and the only variable is k, and as that gets bigger or heads to 0.
Right. This is an increasing term, better than a constant. As k gets bigger, this goes to 0. So this whole thing is O of 1. So that justifies that the average cost of an add last in an array list is constant time. Now, when would that be of no comfort? When do you not care about constant time? When do you really care about worst case? When would it be bad if the occasional add last operation took a really long time? Yeah?
You're flying a spaceship
okay? If you're flying a spaceship and you got to calculate the thrust at every microsecond, and all of a sudden you've got to calculate thrust, and uh-oh, this time it takes a second. Or you're controlling a nuclear reactor. So in real-time situations, so real-time programming, you might not want this to happen. But if all you care about is the average time it takes, then it's fine. Do you have a question?
It's just if you keep the array small, if it ever gets above a certain size with it.
Sure, if you keep the array small. But if you really need fast add last, it needs to be fast every time, you use a linked list. But then if you need random access, you've got a problem. Okay, so we put this, the conclusion is, like I said, you can do k add last operations in theta of k time. So the time it takes to do k add last is proportional to the number of add lasts. Or another way of looking at it is, on average, it's constant time. And so that's how I express it up there. So I've replaced, let's see, up there, k add last are going to take theta of k time. So the tables aren't the same now. This says k add last, that says add last. But if I said add last average, it would be theta 1. So the differences that remain are dynamic array is better at random access, the theta of 1. The linked list is better at insertion. In the middle of an iteration, you got theta of n right there. So that's the fundamental trade-off you have. Okay? So there'll be an assignment, one of the assignments next week will be to do an analysis similar to the one I just did, just with different assumptions. So be warned. All right, let's take a break and look at something different. Always a problem.
It's been perfect. Yeah.
Think about it.
I haven't had any problems.
The only problem is it took me about 3 minutes of fiddling around to get the signal.
Yeah.
Once we get it established, it seems to unless someone kicks the cable.
That's what we're thinking.
I took that plastic roll thing out. Just take it to the space.
Yeah, and we, I don't, it's not, so when most people aren't walking back and forth here, you know,
Be careful.
I should do a sit right there. Like this.
I'm sorry.
Yeah, well, I was like,
I would start with 2. Start with
it was when I got there.
100%. Yeah, you want to systematically go.
Yeah, and so it's.
I do it until I get tired of waiting for the next number. Eventually it'll get tickety. So maybe 8. If you can get that. Look at the table that I put in my slides. Your table looked like.
Very helpful.
No, it's not it fair.
Yeah,
I got my best friend, and she had,
Right now.
and we went to go see my next, and I was like, hey, just shave my head. And so we did that, and then we were talking about
So can you, how are you able to deal with the screen? Are you following along with your computer?
no, I just go back and then pull the slide down.
Just listening?
A lot of this is reviews. Reviews for me.
That was a 10. All right, let's get going again. All right, now, the next major thing you study in data structures are sets. And a set is unindexed, unlike a list, and don't have duplicates. The fundamental methods we're going to assume we have right now are a way to insert an element into a set, a way to remove an element from a set, a way to look up an element, mainly just is it in there or not, and a way to iterate through the set. So why are we willing to sacrifice indexing? Seems kind of useful. Yeah?
Because you don't always need it.
Well, you don't always need it, but why not have it in reserve here?
Because we can make several things faster by not having it.
So by getting rid of insertion, we can make these other operations faster. That's the thing. If you want to go, for example, imagine doing a lookup operation on a list. Does the list contain such and such a number? You'd have to look at every element, so it'd take linear time. Whereas we can do that much faster with binary search trees or hash tables. Okay, so one thing you looked at was binary search trees. And what you should remember about that is it's a binary search tree is, first of all, a binary tree, where every node in the left subtree is smaller than, so if we're looking at the root here, everything in the left subtree will be smaller than 5, everything in the right subtree will be bigger than 5. I won't get involved with what happens if there won't be equal keys, I guess, because it's a set. And that holds for every node. So everything to this side of 2 is smaller, everything on this side of 2 is bigger. And all the operations, insertion, removing, and lookup, involve walking the binary search tree, and I'll remind you what that is. When you iterate, you do an in-order traversal. So you recursively traverse the left subtree, then you visit 5, then you visit the right subtree. So all these would be, if you're iterating through it, you would get them in order. Because you visit everything to the left, then you visit the node itself, then you visit everything to the right. And the pathological case for a binary search tree is what a student of mine once called a binary stick. It's when it degenerates into a linked list. So imagine you'd have a binary search tree that went 1, 2, 3, 4, 5, 6, 7, 8, 9, with no branching at all, just a straight shot. And suddenly, these operations break down and become linear time because to get the good behavior, the tree needs to be nicely balanced. So let's see what we remember about these operations. What's the best case for insertion?
1 second.
Okay, so constant time, when would that occur? Tree of size n. What kind of tree would you have to get constant time insertion? Because insertions always happen down here at the fringes. Okay, I think I got ahead of myself. I thought there was something on the next slide, but it's actually on this slide. Let's remember what binary lookup looks like. So to look up a 9, how do you do it? Right? So you start at the root, you compare the 9 to the root, and if it's bigger, you go right. You compare the 9 to the 8, still to the right, and there you found it. Okay? So you'll end up walking one branch, possibly all the way to the end, or you might find it sooner. Okay? What about inserting 4? So you basically do a lookup. So we look up 4. So we look up 5, it's smaller, so we go to the left. We look up 4. If it's bigger, we go to the right. 4 is bigger than 3. We want to go to the right, but there's nothing there, so that's where we do the insertion. So that's what I was saying. When you do an insertion, it always happens down on the leaves. So if you have a balanced tree, you're going to have to descend all the way to the leaf level in order to do the insertion. So the best case for insertion is constant time, but what type of tree is the one where you get constant time insertion? Yeah? Yeah, it had to be a binary stick kind of thing. Think about, the assumption is we got n elements in the tree. If the tree is completely balanced, how long is it going to take to do an insertion? Log n, because you have to get down to the leaf level. If you got a binary stick, you may look up and do the insertion at the very top. On the other hand, if you have a binary stick, how long could it take to do that insertion? Linear. You have to get all the way to the bottom of it. What about a remove operation? Yeah, so again, as a binary stick, you may look up and remove something near the top, or you may have to remove something at the bottom. Same thing for lookup. You may find it at the top, you may find it at the bottom. What about the cost of iterating through?
Log n.
Well, it's got to be bigger than log n, because we have to visit everything in the tree. Yeah, it turns out it's linear, but it doesn't matter how the tree is shaped. You can always do an in-order traversal of a binary tree in linear time. Okay, so that's not so good. That's no better than a list. Yeah?
So only when we balance our binary trees to the worst cases become log-based too.
Right. So what we'll see is that when you have balanced binary search trees, when you take steps to make sure that your trees stay roughly balanced, then we get rid of these worst cases here. These 3 worst cases become, the worst case for all of these is the cost of working your way down to, well, the worst case for insert is working your way down to the leaf. The worst case for remove is working yourself down to the leaf, assuming you got to remove a leaf. And for lookup, the same goes. So these become log n. The depth of it depends on the maximum depth of the tree. The maximum depth of a binary search tree is log n, roughly. But some of these best cases go up. So what would happen to the cost of insertion if we balance the tree? You still got to get down to the fringe in order to do the insertion. And if it's balanced, you're guaranteed that you're going to have to go at least log n down. So this goes up. These other things, I don't think are affected because you may do the remove or the lookup high in the tree.
And then I assume we also have to consider the cost of actually balancing the tree.
Right, you got to make sure that when you balance the tree, you don't want to increase the cost of the insertion to balance the tree. It turns out you can do the balancing efficiently. Okay, then there are hash tables. This is one way to do a hash table. You take the thing you want to insert, you hash it. In other words, you convert it into an array index. Various ways to do that. And you store the element in the bucket that corresponds to its hash value. So here I'm using, can you figure out what my hash function is here?
The primary element.
Yeah, so what I'm doing is I'm hashing integers using their last digit. I take the number mod 10. So 50 went to bucket 0, 41 and 81 went to bucket 1. I'm not claiming this is a good hash function, it's just easy to illustrate on the screen. And then one problem with a hash table occurs when as you add more and more elements to the hash table, what's going to happen? Well, you get collisions here, 41 and 81 in the same bucket, so you make a chain. What's going to happen when we add 1,000,000 things to this hash table?
You're going to have a second list of each.
We're going to have really long lists. We're going to have lists that average 100,000 each in each bucket. And the performance just completely degrades. So how do you deal with that? Yeah?
Oh, you have like so if you like use lists, then there would be like a load factor, and then based on like the average length of lists, then you like rehash.
Yeah. So what he said was, it's a lot like the array list we just talked about. Once these lists start to get too long, you just double the length of the hash table and rehash everything into it, thereby reducing and cutting all the lists roughly in half. So periodically, you just throw up your hands and make it bigger. Now, for form well, it depends on the quality of the hash function, and that's, it can be tough to, most of us use a hash table, we just use the built-in hashes for the types we use. Designing hash functions is not easy. So, what's the worst, the best and worst case behavior here? What's the cost of the best case for an insertion into a hash table? Constant time, which would occur when, let's say we hashed 22 and it went to bucket 2. There's nothing there. So we just add it. Don't have to look anywhere else. So that's constant. What's the worst case? Right, if we're so unlucky that everything hashes to the same bucket, to do the insertion, why do we have to follow that whole list? Why not just add to the top of the list? Because it's a set. We've got to check for duplicates. So we've got to at least look at everything in that bucket. What about the cost of a remove? We may get lucky and it's the first thing in the bucket. Or we may get unlucky, everything's in the same bucket and it's at the end. Or a lookup, same thing. We may find it right away, maybe everything hashed in the same bucket. We have to look all the way to the end. Iterating through just depends on the number of elements. You have to be a little bit clever to make that work. Because you've got to look at each element, plus you've got to iterate through every element of this array. But it's possible there's a way to thread them together so you don't have to worry about the number of buckets. But anyway, that looks bad too. So we compare them. They don't look any better than lists. And the problems come for two different reasons. The binary search tree is bad because trees become imbalanced. Hash tables, if everything hashes to one bucket. So how do you cope with that? How do we make binary search trees behave better? By using balanced trees. So, did you study a balancing operation in 2420?
Yeah.
Okay, which one? Okay. There are lots of algorithms for balancing trees. But most, or if not all of them, depend on doing rotations. So what the different algorithms are just there to, you add extra information to the nodes of the tree so you can determine when it's time to do a rotation, to bring the tree more into balance. So let's suppose this tree is out of balance. And the idea of a rotation is we've noticed that the tree rooted at 2 is out of balance. The right subtree is a lot bigger than the left subtree. So we're going to rotate and make 5 the root and 2 the new